Let's talk about energy. Though I have to admit, it's raining today. I'm sitting here making my lectures, trying to be cozy with, a blanket and long sleeves and stuff. And I feel my energy levels are not very high right now. I feel like being cozy. But what is energy? Okay. Energy is the capacity to do work. So we have two main types of energy, kinetic energy and potential energy. And then we have a third type of energy that is thermal energy. So when we talk about kinetic energy and potential energy, what we're looking at is something in motion or is something going to be in motion? Does it have the potential to be in motion? So if I am moving and I'm walking along, okay, I have kinetic energy because I have energy due to motion. Or if I have a ramp and something is rolling down that ramp, the object that rolls down that ramp has kinetic energy because of that motion. Now, potential energy, stored energy, so relative to its position. So if I have two shelves at different heights and I drop something from one shelf or I drop something from the other shelf, the objects will possess different levels of potential energy based on where they're dropped from. And then thermal energy, this one has to do with heat energy. So we typically measure these things in joules or calories. Okay. And so that combustion of propane, we get our propane and our oxygen gas. We have carbon dioxide, we have water, and then we get heat and light, which got covered up over here. Okay. So there's an energy change there. Okay, we can look at our chemical reactions with two different types of energy, ones that give off and ones that need energy in. And so we can look at this in terms of heat energy. So we have exothermic processes, so exo, outside. So exothermic reactions give off heat. Endo, inside. Endothermic reactions need heat put into them. So if I think of something like this solid water, so when I have a chemical reaction, if I have S and if I have that L, okay, so if I have solid water, well, it needs heat in order to melt into liquid water. And so that would be endothermic because the solid water, the ice, would be absorbing heat from the surroundings in order to melt into the liquid water. For something like this one over here, the exothermic process, I have the CH4, which is another hydrocarbon, right? So hydrocarbon, again, carbon and hydrogen. This is methane. Okay, so methane combusting in oxygen, we end up getting carbon dioxide and water, and we are outputting heat, so it's exothermic. Okay. So we have a couple of conservation laws that we have to keep, forefront here. We have the law of conservation of mass and the law of conservation of energy. And so we're talking about non-nuclear reactions, which we're not dealing with nuclear chemistry here. We're just looking at regular old chemical change. Okay, so for conservation of mass, for a non-nuclear change, mass is neither created nor destroyed. What I put in is what I should be getting out. So the sum of the masses of my reactants should equal the sum of the masses of my products. So energy, okay, in a non-nuclear change, same thing. Energy is neither created nor destroyed. Now, something to keep in mind though is as we do reactions or as energy is involved, well, we're human beings. We're not perfect. And so things happen throughout our reactions. Like let's say I'm doing something that's in multiple steps and I have to transfer from one beaker to the next and then one beaker to the next. Well, maybe I lose some stuff along the way. I haven't destroyed, any of my stuff, but maybe stuff gets left behind on the side of a beaker. And so as I transfer from one container to the next, it seems that I've destroyed something, but I really haven't. I've just left something behind. Or sometimes when I'm doing reactions, I can end up in a situation where side products form, or maybe I leave it sitting out and I end up with dust that gets in it, or something is incomplete. And so it can artificially appear as though something has been created, but it hasn't. It's just other things that have happened during my reaction. Now, when we look at energy, okay, when we are transferring energy from a power source into, say, our houses, there's a lot of places along the way where our energy can get transformed in different manners. So let's say we take some natural gas and we boil water, and then that water vapor causes a turbine to turn, and then that turbine spins a generator, and that generator creates electricity that goes to our houses. Well, the amount of energy that's output by the generator is not necessarily the amount of energy that gets to our houses, because things can happen along the way. We can definitely end up losing some of the energy that we could utilize due to heat. So I have my cell phone right here. All right. Now, how many of you, when you have been using your cell phones, have noticed your cell phones get hot? Okay. Well, your cell phone gets hot, you might also notice that the battery indicator on your cell phone starts going down a lot faster. So what's happening is as your battery is working, most of that battery work gives us the electricity necessary to run our phones. But sometimes we can end up with that reaction generating heat. And so instead of getting the maximum amount of electricity, we end up with a situation where some of the byproduct of that reaction is now heat instead of the desired electricity. And so we end up having our battery deplete faster because some of that energy is coming forth in the form of heat instead of the electrical energy that powers our cell phones. So we still have those conservation laws. There's just other processes that can happen that means that it's not always as efficient as we would like it to be.